So first of all, this talk is not so much about process modeling, it's about process modeling technology. And this is our definition of process modeling technology. It's general methodologies and systems for the efficient and effective, first of all, capturing the available knowledge in the form of mathematical models. So process modeling technology does not create new science, it captures what is there already. Deploying this knowledge for engineering across the process life cycle, and then identifying what the gaps in the currently available science are. So process modeling doesn't create new science, but it helps guide science with an engineering objective. We are talking about a different set of industrial sectors, as shown at the top right there, starting with upstream oil and gas, getting the oil and gas out of the ground, refining the oil and the gas, then the main chemical and petrochemical industry, and then we go into all sorts of things, including pharmaceuticals, agrochemicals, food and beverage, specialties, and so on. Power in various forms is part of these process industries in the sense, for example, of not only power generation, conventional power generation, but the nuclear industry, nuclear fuel reprocessing is one of the main applications of this technology. And then, of course, this links up with mining, metals, and so on. So a different set of industries to what we've been hearing this morning, mechanical, electrical, aeronautics, but nevertheless, of course, a very challenging environment. For starters, we don't know what a linear system is in process. We never, ever look at linear systems, not even as approximation, because it really is all the processes are non-linear for various very well understood physical reasons. Okay. Now, this is a picture of a process modeling and the ambition we had in the 90s. That is actually taken from my inaugural lecture at Imperial a very long time ago. And really, where we are nowadays is somewhat more complex systems, and you will see pictures like this or systems like this throughout this presentation. So the real challenge for us is complexity. Okay, and definitely speaking for myself, I spent my whole life battling against complexity, how to handle complexity. Okay, is complexity in the concepts and complexity in the computations. Okay, so in terms of an outline for this presentation, it's two parts: where are we now, and where are we going to next? Nobody's been in this industry for very long, would venture to go beyond a decade forward in predictions. So this is what I'm going to do to focus myself on, what's going to happen in the next decade in terms of predictions, and then we have some conclusions. For those of you who want to switch off at this point, my conclusions are very similar to what you heard from Carl Johan Armstrong. So, we did not communicate before, yes, and I didn't change my slides during lunch. Okay, so where are we now? Okay, if you try to understand process modeling, a very good starting point is along these three axes. Okay, the first axis is what part of the universe are we trying to model? Okay, and this could be anything in the case of process, from a single catalyst particle to a tube in a reactor packed with catalyst, to a reactor unit which may have 30,000 such tubes, to a plant which may have this reactor unit together with many other things, or many copies of this as well, to multiple plants linked together. Okay? So the first question I always ask, whenever someone talks to me about a process modeling tool or a process model, is this question: what is it focusing on? What part of the system? Okay? The second question you have to ask yourself is, what degree of physical detail are we putting in? Okay, and there's different dimensions in this, but here I chose to look at the spatial dimensionality. So we can have lump systems, which are just, of course, ODEs or DAEs, to one-dimensional, two-dimensional, three-dimensional, four-dimensional. I'll show you a four-dimensional system in a second. They're fairly routine these days. And then the third dimension is, what do we actually do with this model? Okay? And there we have to follow the model along the process life cycle, from the early stage R&D, when we try to understand the chemistry on a catalyst particle, all the way to real-time operations. Okay. So what's been happening out there? What are the key drivers right now along these three dimensions? And the first driver has to do with component model detail. I mean, essentially, building models of the kind that I'll be talking about is a very long, arduous, and expensive business. So the minimum requirement is that you want models which are predictive, okay, they predict the impact of external inputs and disturbances on the key performance indicators within the accuracy required by the business objectives. Okay. In very practical terms, what this means is we are looking for more and more and more detailed physical models. Okay? So let me illustrate this. This is a multitubular three-phase catalytic reactor. It sounds so strange. In fact, most of the reactions, the exothermic reactions in the chemical industry are performed in systems like this. You have the tubes packed with catalyst, okay? And the reaction produces a lot of heat, and then you have to get the heat out from there, okay? So this is the model of the tube. It's one of those. There are 30,000 of those, or 10,000, or 40,000, something like this, okay? The tube is surrounded by coolant fluid like this, and then inside the tube, I have catalyst pellets. This is not drawn to scale, by the way, the catalyst pellets of millimeters and so on. But anyway, if I take one of those, this is a catalyst pellet. It is surrounded by a film of liquid or gas in the system. It's called catalyst pores. Okay, here's the catalyst pore. The raw materials have to permeate through this film here, then they have to diffuse through the pores, at which point they find the active catalytic sites, there is a reaction, and then the products make their way out, okay? Now, the products, this is a standard, for example, technology for Fischer-Tropsch synthesis. The product itself is actually a distribution of molecular weights, carbon lengths. So what do I have here? One dimension is axial variation. Second dimension is radial variation. Third dimension is intraparticle variation. And fourth dimension is the distribution with respect to the molecular weight. This is a four-dimensional model. Now, if you really want to predict how a Fischer-Tropsch reactor behaves, this is the degree of detail you have to go. How do we know? Because we tried the lower degrees of detail for several years, and then we didn't get very far. So this is not theory. This is the kind of models, for example, that companies like Shell are using in their Qatar plant, gas to liquids, to actually predict the behavior. So what happens on a scale of this monster here, which is 8 meters diameter, 22 meters tall, you can see them there, 1,200 tons, is actually determined by the physical phenomena on this scale, right? We have the models nowadays for doing this. However, you can imagine the computational complexity of a model like this. It's a four-dimensional integral partial differential algebraic equation. Okay. So at least we know that the components predict what they should predict. Okay. Now, the second pressure we are under is to expand the boundaries of the system to the right. And the reason for that is, many people understand that it's not really very meaningful to try and optimize a single unit on its own. Optimizing a single unit on its own may come up with a solution which is optimal for this unit, but from the point of view of the overall system, is suboptimal. This is not the point I want to elaborate too much in an audience like this. But to cut a very long story short, what they are being pushed towards is towards the right of this picture, looking at bigger and bigger envelopes. Now, the problem we have is that we are simultaneously looking at bigger and bigger envelopes and more detailed models. Is this right? I mean, this is just something I've just made up to impress you. So here's a case study that has been published by Shell a few years ago. What they are looking at is optimization of the gas production and processing in southern Iraq. Okay? So what they are looking to do is to study a system like this, where we have a number of oil fields producing associated gas. Okay? We have a number of processing facilities. They are all connected by these lines here, which are actually pipelines of tens of kilometers long. And what we try to do is to optimize this system on a daily basis. Now, of course, companies like Shell and the oil companies in general have been solving models like this forever, since the 60s, in fact. But the way it has normally been done is by using simple linear models for the individual components. What they're saying is the problem with that is you solve the model very easily. It's linear. It's just an LP. You get the optimal answer. When you try to implement the optimal answer, you may find that it's unrealizable. It cannot be implemented in practice. So what we're looking for is to put in these models here a degree of detail which, until recently, we would only be able to put in a single plant. So what you see here is the same model, but now inside the modeling environment. This is a GPROMS process builder. And each one of those blobs is a compressor station, and they are the pipelines. These little things are tens of kilometers long, and these are the various plants, and we are looking at the whole system as a whole. And it's not just a picture, because if I zoom in into the individual bits and pieces, we have a higher degree of detail in there okay, resolution, and so on. So as I said, this system being optimized as a single entity, right? We are all into maths here. It's a static optimization, I should say, 300,000 equations, okay, non-linear equations. We're doing optimization every few hours, 77 decision variables, 32 important constraints. Okay, so a lot of complexity. Is it worth it? How does the answer compare between this and some kind of nominal answer that we would use in the past? Okay, it's very unusual to find published figures for this, but we are looking at 4.9% profitability. Now, in this particular case, it wasn't disclosed what the actual number is, but it takes a simple calculator from the basic knowledge of costs of things to work out this is more than $100 million per year. This is the kind of thing we're looking for. It is worth it if you can do it. So we're pushing the envelope. So this is what's happening along here, but now we have a new dimension there. Because if you're producing simple materials like ethylene or nitric acid or ammonia, it all finishes when you produce the right material of the right quality at the right price. But if you're producing more complex things, like pharmaceuticals, the real test actually starts after the product leaves the manufacturing site. It's when you swallow the pill. So it goes into the stomach, it disintegrates within 15 minutes approximately, you get the crystals of the active ingredient, and then those crystals of the active ingredient go into the gastrointestinal tract, and they slowly dissolve and they diffuse through the walls of the intestine into the blood circulation. So we cannot optimize the manufacturing process without actually looking at what effects our manufacturing decisions have on the in vivo performance of the drug. So the current boundary of process modeling is like this, okay, where we model the various manufacturing steps. This is a gross approximation. In reality, there are many, many more steps in between. But then the important thing is we actually model the oral absorption inside the intestine. The biology of that, okay, is pretty well known. We can actually have models which do this. We have models nowadays which can tell you whether it's best to take a pill before or after lunch. We have models which tell you whether it's best to form large crystals or small crystals here for that thing, okay? Don't want to go into the details here. There is a lot of things which have to be done with complex material structure. That is not just a flow rate. Karl-Johan, you spoke about the information, going from bond graphs to having something which is more representative. Well, this is the next step up, where it's not just flow rates and compositions and so on. We have if you look at down here, you have a distribution of tablets. Inside the tablets, you have a distribution of granules. Inside the granules, you have a distribution of particle sizes. And then inside the particle size, you have impurities. And the models we are looking for are of that level of complexity. So this is what we are up to in this case. And the third dimension I should mention is, so you've got the very detailed models over increasingly wider envelopes, and then what they're trying to do is reusability. The cost of developing a model, any of this kind, is too high to be sustained by a single application. We cannot afford to build a model of that detailed model of the reactor, use it for engineering design, then throw it away and do something else for operations. So we want to push this model across the process life cycle. So this is the process life cycle. It's a very standard diagram which starts from early stage R&D, engineering design, operations. One of the biggest advances in recent years is the extent to which we are increasingly able to take models, detailed models like the ones I mentioned before, and push them into the operations regime, okay? So in operations, I mean things like monitoring the equipment, monitoring the activity of catalyst, soft sensing, of course, state estimation in this community is very obvious, to all the way to things like nonlinear MPC. And if you take a classical hierarchy of control, we're now beginning to be able to take detailed physical models and use them not at the level 1, which is a DCS. DCS is well established, there's nothing you can do there. But going up one level, for example, nonlinear MPC in polymerization plants, real-time soft sensing using very detailed models of olefin plants, real-time optimization, including discrete decisions in utility plants, monitoring of coking and catalyst activity in olefin plants again, and so on. So this is the kind of thing which is becoming routine. I was very, very interested to see your point about taking models closer to the DCS, and we have a talk after this on this. So this is where the next frontier is, and we're beginning to get in there. The key point here is that we exploit the process knowledge, it's just marketing speak for scientific models, okay, to essentially improve the quality of the results, as obvious. But one thing which is not quite so obvious is that in some cases, the cost of deployment of a solution which is based on detailed physics is actually less than going to the plant and kicking the plant around for 3 months to build a response-based linear model. So I may come back to this at the end. So this is really where we are now, okay? And the question is, what is coming next? And of course, the buzzword through our industry is Industry 4.0, digitalization, and so on, a lot of which is hype. Now, the question is, what isn't hype? Okay, and what isn't hype is the same as asking what is new. What are the things we can use in our kind of technology? Now, I mean the inclusive hour, you know, Modelica, Dymola, GPROMs, that were not possible before, were not available before. So undeniably, we have advances in 3 different areas. One is data. We have a lot more data. We are measuring a wider range of quantities like compositions. I know this is not very relevant to you, but composition is one of the biggest problems. The sensors are higher quality, but the most important thing from the point of view of software engineering, people like myself and many of you, is these data are accessible. I can write an app here, and I can access, with the right permissions, I can access that temperature on that plant in the Middle East right now. And that is very important from the point of view of developing sophisticated applications. The second area there is computation. Of course, we have much more powerful computers at lower cost, so on. We have high-performance computing nowadays. Even on a machine like this, I have 4 cores, and that's nothing. We also have more flexibility. And the cloud, again, is another one of those much hyped concepts. But from a very practical point of view, one thing that the cloud does is I can take my credit card out, I can go to Amazon Web Services, and I can secure 1,000 cores for the next 2 hours to do a big computation. And that really changes things, as you will see with some of the things I'm going to show you. And of course, finally, algorithms, not the kind of algorithms we've been developing, which we've been doing for a long time, but algorithms which are mainly in data sciences, data-driven modeling, hybrid modeling, surrogate model data mining. I will talk about this in what comes next. This is not revolution. It is actually evolution, going back to some of the definitions we heard today. It doesn't matter. The key point is that all of these things have reached a point where they're applicable to practical problems. And the question is, what can we do with this? Now, one of the things we want to do is answer some of the questions which were raised in the sort of previous presentations. And some of them did have to do with what we could call understanding system, global system behavior. If you look at the way we use modeling nowadays, what we have is a system like this, a system model. We have various inputs, and the only inputs we really care about is things which are under our disposal, decisions, and things which are not under our disposal, like external disturbances, commercial environment, like prices and so on, market availability and so on. And then a model is simply something which is a mathematical function which relates this and this to the key performance indicators of the process, the product quality, performance, the operability and safety of the process, environmental impact, and so on. If you look at the way we use modeling nowadays, what we do is point calculations. We pick certain points here, okay, and then we map them into, we solve the model, we map them onto the KPIs. This is really how most modeling is being used nowadays. Now, this is a huge waste of opportunity for something which cost 6 months to develop and $500,000. What we really want is to move to a different kind of paradigm, where we're interested in the behavior of the system, not at certain point decisions, but over the entire decision space. We recognize that the external inputs, the environmental inputs, are probabilistic, okay? And then, of course, if we do this, the answer we're going to get isn't going to be a point, it's going to be a probability distribution. So what we are looking for is probability distributions which quantify the extent of risk you're taking in basing any decision on these calculations, okay? We also have tools like global sensitivity indices which say which part of this variability is due to this or to this. Of course, once you have models, the thing you have to recognize is that there is a third source of uncertainty. And that is, of course, the fact that the model itself is uncertain. Okay? And of course, we are all used to having parametric uncertainty being described by covariance matrices and so on. I don't want to go into the details here of how we do this, but establishing these kind of variability measure is one of the key challenges for process modeling nowadays. It's very easy for us nowadays, because we have the algorithms, we have the library models and so on, it's very easy for anybody to put together a model of pretty much anything. Too easy. The real question is, do I believe the answers? Okay? So being able to quantify this is a key part of the equation. I don't have time to go into how we do this, but a lot of this relies on fairly advanced techniques for parameter estimation, like frequentist techniques like maximum likelihood, or designing experiments, and so on. Now, increasingly, if I go back to this, increasingly we are moving to a different paradigm. We are relying more and more on Bayesian estimation approaches. I don't know, but I suppose that many of you, most of you, will be aware of the fact that this is a gross approximation of the uncertainty in these parameters. There are techniques, things like Markov chain, Monte Carlo, nested sampling, and so on, algorithms which actually quantify the true uncertainty or probability distribution of the parameters. And they don't look like this. This is what they look like. They are not regular sort of multidimensional normal distributions. We can compute this at enormous computation. And this is where the new technology comes in. The fact that we have high-performance computing, which allows us to do intelligent sampling of the input space. It allows us to compute this kind of thing here. We have techniques like data analytics, data mining, which allow us to analyze the inputs that go into this calculation. It's not a question of putting it into a calculation, it's analyzing the inputs, okay? So this is translated into practical tools, and we can sort of look at variation of uncertainty over time, okay? I don't want to dwell too much on this, but we're beginning to have practical tools which do this. They rely on this massive increase in computing power, okay? So having more computing power isn't about doing the sort of things we used to do before, and it took 5 minutes and now it takes 2 seconds. It's about doing things which were not possible before, okay? The other area, which I'd like to touch briefly upon, is the impact of advances in data science. Already we had a discussion here about data-driven approaches and so on. And of course, the story of the data-driven modeling is a very tempting one. It's such a simple story. We have a plant. We have all these sensors now. I mentioned we have much better sensors, much more of them. We collect this big data. We do machine learning, and we get a model. This model, to be honest, is just a mapping, mathematical mapping between inputs and outputs. Nobody says that it has to be physics-based. So everything we do, simulation, optimization, global system analysis, and so on, is still valid. So what's not to like that? And more to the point, anybody can very easily do this. Okay? We've got the data. We've got standard algorithms in Python, scikit, MATLAB, and so on. We can just do the analysis. We get the model very quickly. Okay. Of course, as many of you suspect and know already, this story isn't 100% accurate. It's not a question of whether I can get a model. Of course I can get a model. The question is, how useful is this model? Okay. And really the question is the fact that, first of all, the inputs and outputs, the U's and the Y's in this model, by definition, are what I can measure. But very often, the KPIs I'm interested in are quantities that I cannot measure. So that is a bit limiting. The second thing, of course, is, again, most of you will know, is that I can only use this model within the range of variability of the inputs that is represented in the data. Basically, it's very dangerous to extrapolate this model. But, so those two are pretty obvious points. The third point is not quite so obvious, that having a lot of data is not the same as having a lot of information, especially in continuous processes, where the main objective of the plant manager is to keep the plant steady at the same operating point day in, day out. You may have gigabytes of data which contain extremely limited information. There's no statement I can quote you from real presentations of real companies who have found this the hard way. So we do not think that this is the way to go. The way that this makes sense is in the context of a hybrid data-driven physics-based modeling, where we use prior scientific and engineering knowledge, i.e. the kinds of models we have already, okay? our philosophy has always been push the physics as far as it will go, then use a data-driven element to patch the gap between the best physical model and the reality. Okay? There are different approaches, which is start with a data-driven model and introduce the minimal amount of physics to make the model realistic, like mass balance and so on. It's just philosophy, but my philosophy is always go maximum physics and then patch it with data. Okay. So one way or another, either by physics alone or by physics and a data-driven element, we have models nowadays which are really predictive. Okay? And that is actually true for most of the sectors I mentioned before, the industrial sectors. So what is the problem then? Are we done? The problem is that the model may be predictive. It may cover the right scope in terms of the part of the universe that it models and so on, but it may be unsuitable for some of the applications we have in mind. I mentioned before about the idea of taking some of these models into real-time service, online operation. Obviously, that implies a certain degree of both responsiveness but also robustness. You don't want applications failing in the middle of the night at the middle of the desert. Okay? Also, in some cases now, although we have made so many advances in terms of computation and so on, our ambitions grow faster than our capabilities. So, for example, nowadays, a lot of the countries in the Middle East have begun to take a very global view of the entire country, basically, and they want to do country-wide optimization in a single go. Just like the example I mentioned in the beginning, but probably an order of magnitude bigger. And in this case, what we need is model reduction. That's the term you used. And here, one approach you'd use is by trying to generate surrogate models, take advantage of the technology that we have already. So a surrogate model is just an explicit relation between inputs and outputs, explicit algebraic relation, at least for static models. For dynamic models, it could be slightly different. The example I have here is a real example, disguised and so on. It's something called a GOSP, gas oil separator. It's something which we can easily model from first principles. The problem is not that we cannot model it. The problem is we have systems which have 100 of these plus many other things. So if we put the whole thing together, it becomes completely intractable. So what we have in a typical unit like this is 5 inputs, one of which is discrete value. It takes values 1, 2, 3, and 4, and 14 outputs, which are continuous. And we have technology nowadays which basically, first of all, creates a lot of data by sampling the detailed model, okay, using the techniques I mentioned before, global system analysis, and then automatically derives a model with a guaranteed accuracy over a certain domain space. Here, the algorithm I'm showing is by Nick Sahinidis of Carnegie Mellon University. There are many other algorithms for surrogate modeling, but this is the one we have most experience with, I should say. The algebraic form and the sort of basis functions is determined automatically, and we have models now which we can take. So we can throw the detailed model away here, and we can use these explicit expressions, and that makes a huge difference in this. This is core technology. This is not just, it's an analysis algorithm and so on. It's core technology for the way things are going, because the story I'm giving you is one in which we go for the maximum physics over the maximum scope. Inevitably, that's going to result in models which could be computationally intractable. This thing allows us to break the link between computational tractability and predictive accuracy. Okay, so at least speaking of myself and my group, we are putting a lot of emphasis in this technology. So to conclude, we've come a long way, definitely. If you compare where we were in the 90s, this was pushing it, I think, and we can do some extremely complex applications, some of which I showed you here. If I sit back and think, what is it that made the difference here? It's, in my opinion, the 3 things we mentioned there. Number 1 is declarative languages. Without declarative languages, like Modelica, like gproms and Speeda before it, it wouldn't have been possible to capture the knowledge, the state-of-the-art knowledge of these specific disciplines and capture them into models. If I had to write a specific Fortran or C++ or whatever module for each one of them, it would never have happened, full stop. The second development is the fact that we realize that these are not simulators. What we have is a model, and then we can do many different things with the model. We can do simulation, of course, we can do optimization, we can estimate parameters, we can look to identify faults, okay, and isolate faults, we can do the kinds of things we've been hearing about. And of course, the third one is, yeah, we did make a bit of advances in the algorithms underneath the numerical algorithms, symbolic manipulation algorithms. Even to converge the static simulation of something like this has taken a lot of advances there, and of course, the hardware. So where do we go? And this is my last slide. Where do we go in the future? Well, I identified many different things for the future, ongoing developments, and so on. To my mind, the most exciting is this one here. And the picture I showed before, which is about taking detailed models, predictive models, into real-time applications, okay? As I said, from nonlinear MPC, which of course we've known about for a long time, but who could ever get it to work before, to using massive detailed models to monitor the activity of a catalyst in a reactor. So actually, to be honest, we're doing this already. So what's my problem? Well, give me any one of these challenges. Give me a moderately sized model, not a 300,000 equation one, maybe a few thousand equation one, and I can actually do this. So what's the challenge? The challenge is that if you look at the way each one of these applications is being developed, it's developed as a completely different code base. It's a completely bespoke development, okay? Now, these applications are not models anymore. It's not a single model doing a single optimization. If you take any one of these applications, you find that it's a sequence of or a set of model-based applications communicating with each other in real time. So here, even for nonlinear MPC, which is the simplest one, I have an estimation calculation followed by a dynamic optimization calculation. Okay? And if you take some of the others, 2 or 3 applications being coordinated in real time, and very crucially, talking with an uncertain outside world, getting data which may or may not be valid. Now, could we, and this is really the challenge, could we come, just like we came with unified frameworks for modeling 20 or 30 years ago, could we come with unified frameworks for digital applications? Because if we could, we would massively accelerate the adoption of models in these real-time operations. And that is a challenge, obviously something we're working on, but I'm sure you will want to think about this for the future. And if we do this, the impact will be huge. Thanks very much.